Hello everyone, my name is Arjan van Voorden and today we will discuss the future energy system towards 2050 coming from the industry perspective, particularly from the distribution system operator or DSO. In this video we will talk about the different scenarios towards a zero emission goal, and then we will provide a general overview of these scenarios. We will elaborate on how to design the future energy system that includes flexibility options coming from multiple energy system. To achieve a zero emission goal in 2050, we have investigated several scenarios in different levels. The first one is a regional scenario, where a region has many heat networks and also focus on local renewable sources so that they become virtually self-sufficient. In this scenario, citizens are very driven. Another scenario we have investigated is called the national scenario. In this scenario, the country, in this context the Netherlands, becomes a leader in reducing CO2 emissions. Also, the country's focus is geared towards an overall renewable sources. Thirdly, we have the European scenario. In this scenario, Europe becomes a world leader in reducing CO2 emissions, and the focus is on importing biogas. In this scenario, energy-intensive industry is growing. Lastly, the international scenario. In this scenario, the entire world aims to reduce CO2 emissions, where the fossil fuels are severely limited. There is a global market from hydrogen and biomass. The focus of this scenario is the input of hydrogen. In these four scenarios, we have created a scenario space in different directions under the condition of zero emission in 2050. From these scenarios, we have been modeled using an energy transition model, or ETM. Starting first with the mentioned scenarios, with control from region up to international, and then the ETM performs complete energy calculations, which includes electricity, hydrogen, biogas, and heat. Once this is recognized in the model, the Howley profiles are recognized, where it defines the demand and supply in the network, includes its flexibility. At the regional and national level, which includes conversion, storage, and exchange. After the recognition, the local supply and demand profiles are calculated in the existing network for both the TSO and DSOs. In here, issues are found out, such as the lack of capacity or even a need of new analysis. Given the comprehensiveness, the analysis provides measures or adjustment from the infrastructure after identifying the bottlenecks in the network. Finally, the model comes up with development pathways in the near future that includes flexibility, infrastructure, and the impact of these to the current energy systems, including its cost and space. From the four scenarios, the analysis from the model shows that there are significant and big difference between the demand and supply. The supply comes partly from renewables, which is clearly a weather-dependent energy source. If you subtract the demand and supply, you will arrive at the so-called flexibility plot. In order to balance supply and demand, flexibility options must fill in the gap of the discrepancy. If there is more demand than supply, there is an energy shortage. On the other hand, if supply is greater than demand, there is a surplus. Examples of flexibility options that aim to reduce the gap of supply and demand can be electricity interconnection, system batteries, power plants, power to gas storage, or even curtailment. Of these flexibility possibilities, it is worth to note that multi-energy systems are power to gas and gas storage. The importance of these two are imminent in the next years to come, since they hold the key to overcome renewable fluctuations. After identifying several flexibility options, the model identifies which of these choices to use and where it should be located, because specific problems in the network arise depending on the provided scenarios. Afterwards, bottlenecks in the connection points between TSO and DSOs are identified so that solutions are provided in timely manner. Examples of these solutions are coupling stations and timely deployment or flexibility options. Finally, the development pathways are generated in every scenario. The model indicates that capacity of each flexibility options must be installed in the near future, in this case the year 2050, so that the zero emission goal is attainable. Now that we have emphasized the big role flexibility options provide, it is time that we evaluate the impact of these ambitions in terms of cost and space. The current cost of the overall energy system in the Netherlands falls roughly at the range shown in this figure. If we consider into account the cost of each scenario, we see an overall rise in cost as compared with the current one. Additionally, the cost of the networks per scenario is also provided in the model as shown on the right. This includes offshore, regional and national networks, which hold a higher cost share overall. Now for the impact of space, different scenarios provided different results of putting up several renewable plants. For solar plants, for example, regional and national scenario highlights the need for solar parks in this region, where for European and international scenarios there is not much emphasis on solar plants, but the focus shifted to hydrogen. The same is true for wind farms and the gas network for different scenarios, where there is more emphasis on wind farms for regional and national scenarios, while more emphasis is given on the gas infrastructure at the European and international level. Similar situations also arise for the need of space of high voltage substations for both regional and national and European and international scenario. So let us recap. In this video, we have learned that from an industry perspective, it's best to look at the future energy system in several scenarios, ranging from regional up to international. You have also learned that from these scenarios, we can generate possible outcomes by doing comprehensive modeling and then produce development pathways to zero emission. In here, we have learned that the need for flexibility options is imminent in order to balance supply and demand. By making smart location choices for these flexibility resources, we can limit the impact of these supply-demand imbalances in our electricity infrastructure. And in the future, these flexibility options will come from multi-energy integration, such as power to gas and gas storage. And finally, you have seen a general overview of the need, cost, and the space to design this energy system of the future. We hope that you have learned so much from this module and see you soon.